Alright, Chapter 7 talks all about magnets and its uses. And so we're going to start out talking about magnetism. So first of all, a little history about magnets. About 2,000 years ago, the Greeks found a natural mineral. We call that, or they called that, magnetite. And so that magnetite mineral, the Chinese, about in the 12th century, the Chinese basically used that to form compasses that of course they used for navigation, so to help them tour around the world. So it's kind of the general idea of what magnets, how they kind of got their first start. They found it as a mineral. Later on, 12th century, used as compasses. That's kind of the general idea of how magnets got their start. So magnetism, if we have the word magnetism, what does that mean? Magnetism just refers to anything that has to do with magnets. It refers to the properties, the interactions of magnets themselves. Magnetic force. Basically, depending on which end of the magnets you put together, they either repel or they attract each other. So if you have, a north and a north, a south and a south, we'll get into magnets more. It depends on which end you put together, if it's going to attract or it's going to repel. And of course, the strength of that force increases or decreases depending on, if you put them together or you move them apart. And that's that magnetic force. Now, every magnet has a magnetic field. Now, it's kind of a cool thing because if you look at it from a distance, it kind of looks, a lot of people have told me it kind of looks like a spider from a distance. Now, obviously, these lines aren't really here, but it's kind of the visual. A magnetic field is what surrounds a magnet. It exerts a force on another magnet. So this is what causes a magnet to actually attract or repel another magnet. The magnetic field is obviously strong when it's close to another magnet and weak when it's, far away from another magnet. We can draw these magnetic field lines shown here. Now notice something about these magnetic field lines. Look at the arrows. Look here. Look at that. Pretty cool, huh? Do you notice something? Hopefully you're noticing that all the magnetic field lines go from north to south. That's the way the magnetic field lines always go. They go from the north end of the magnet to the south end of the magnet. Always from north to south. The magnetic pole is where the magnetic force is the strongest. This is definitely something you should know. The magnetic pole is where the magnet is the strongest. Okay? All the magnets have a north pole and a south pole. So for a bar magnet, like a magnet like this, the poles are at the opposite ends of a particular magnet. The magnetic field lines always connect the north pole and the south pole. So like I showed you in that previous slide, if we go back here for a second, okay, those magnetic field lines connect the north and the south pole. That's the whole point of a magnetic field. Now, just because you have a different type of shaped magnet doesn't mean that, the magnetic field lines still always connect the north and south pole. And of course, we always have different shaped magnets. We have horseshoe shaped magnets. Okay, so notice here the north pole is up here, the south pole is down here, but look, still, north pole connects south pole. Still, the magnetic field lines connect the north and south pole. You can have disc-shaped magnets. Again, the north pole connects to the south pole. Okay, but notice the top and the bottom are north and south poles. These are what I call like refrigerator magnets, these disc-shaped magnets, if you've ever seen those. In fact, I have some of them in the room where you just put them on the, on a flat surface. Okay, so those are different types of magnets, but notice no matter what, that the magnetic field lines always connect the north pole to the south pole. So of course, we know that two magnets can either attract or repel each other. North pole, North pole, repel. South pole, South pole, repel. North pole, South pole, attract. So notice that if they are different poles, they're going to attract. But if they're same poles, they repel. So, when two magnets are brought together, their magnetic field lines are going to combine and produce one new magnetic field. Now, kind of interesting, as I already pointed out, that a magnetic field has direction. We already kind of pointed on this when I pointed it out. Notice that the magnetic field always goes from the north pole of a compass, north pole to south pole. Okay. Now, this is kind of how a compass works. A compass always aligns itself with the magnetic field lines. So these little pictures here in our drawing are compasses. The red is the north pole of the compass. Notice that no matter where I put this compass within the vicinity of my magnet, that it always aligns itself with the north, with the magnetic field line pointing with the magnetic field lines. So it always goes with the magnetic field lines. So it's always going from the north pole to the south pole. So look at that. It's always going, no matter where it's at, it's always going in that magnetic field line. That's the purpose of a compass. It always aligns itself to the north to the south. And that's what a compass does. So, the purpose of a compass is that a compass is brought near a bar magnet, and that compass needle rotates. And the force is exerted on a compass needle by the bar magnet that causes that needle to rotate. And it basically rotates until it lines up with the magnetic field lines. So, naturally on Earth, the Earth itself is a natural bar magnet. So, we have a north pole and a south pole as far as a magnet goes. So, we have a geographic north and we have a geographic south. But we also have a natural magnet within the Earth itself. And so, we line ourselves up, we have a natural magnetic field line of the Earth. So when we place our compasses, so if we get lost, now we have, of course, GPS, but there are times where you have to go out in the woods with a natural compass. That compass aligns itself with the magnetic north. And so that way, or I guess the magnetic field lines. And so that way it is reading, north, which is actually magnetic, the magnetic field lines. And so it's giving us an idea of what is north geographically. And so it allows us for us to know where are we going. And so it's kind of interesting. What is the compass truly telling us? Well, it's telling us where is truly the south of the magnet. So it's kind of interesting. That's what a compass is truly telling us. It's finding the Earth's magnetic field. So currently the Earth's south magnetic pole is located about 1,000 kilometers from the geographic North Pole, and sometimes it moves slowly, and sometimes they can even switch places, which gets a little confusing, but for right now we're going to know that this is what occurs. Now, you might have noticed that a magnet will not attract all metal objects. So if I try to take a magnet and attach it to some things, like for example, if I try to attach a magnet to my dry erase board, sometimes it won't happen. It just depends. Only few metals such as iron, cobalt, and nickel are attracted to magnets or can be made into permanent magnets. So what makes these elements magnetic? What actually makes them so that they can turn into magnets? Electrons have magnetic properties. So the key with anything is the electrons. That's what gives things their magnetic properties. In the atoms of most elements, the magnetic properties, the electrons cancel out. So for most things, they cancel out, meaning that the electrons cancel each other out, and so there's no magnetic properties, there's no big deal. But in the atoms of these certain elements, iron, cobalt, nickel, some of these different elements, the magnetic properties don't cancel out, which gives them this special magnetic ability. And even though these atoms have their own magnetic fields, these metals are not always magnets. So even though first of all then, okay, they have this ability to be magnets, that doesn't always mean they are magnets. So the electrons give them the ability to be magnets, but they don't always become magnets. So they have step one, that they can become magnets because they have the special electrons to become magnets. But then you have to not only have the special ability, sorry about that, they also have to have the next step, and that's called the magnetic domain. Within each particular element, you have these groups of atoms, and they have to have this certain alignment. You think about it like desk in the classroom, how they're each all perfectly lined up and everybody's in their certain seat. Well, you have to think about it like it's a huge, ginormous classroom. So there's an enormous, large number of atoms. And of course we can't see them because they're too small. But they're all aligned, okay? And in order for them to act like magnets, they have to be aligned in a certain way in order to behave like a magnet, in order to have a north and a south pole, okay? And this makes a certain domain, okay? And this will make more sense here when we look at a picture. Okay, and so the domain has to act one way in order for it to be a magnet, and it has to act another way in order for it to not be a magnet. Okay? Alright. Alright. So, here we have a very random, messy domain. So this is what it looks like when you guys decide to all work in groups in the classroom. Very random, very messy, disorganized. And so this would be an example of it basically canceling everything out. So this would have no magnetic properties whatsoever. So this would be an example of a domain if everything's all messy. Sorry, I don't know what's going on with my computer. Oh. This would be an example of a domain that has no magnetic properties. So if you're all messy in your desk just working on like a worksheet or something, think of it that way. Okay, they're all not lined up, they're not all perfect, they're just kind of scattered all over the place. Okay, notice that, look here, see like the north and south are just kind of everywhere. Okay, there's no perfect alignment to them. This would have no magnetic properties, they're just random, they don't cancel each other out. Okay, versus look at this picture. Okay. Okay. This here, look how nice and pretty they are. Look how this would be like an example of like you're in a lecture style class, or you know, when you come in the room, how everything is nice and pretty. See how like the north and south, look how nice and pretty those are. Look, they're right next to each other. Okay, they can cancel each other out because they're so close. Look, I guess it's okay, everything is real nice and pretty to each other. Okay. So this would orient themselves real organized, and so they would cancel each other out. And so now this one would be an example of a domain that would have magnetic properties. Okay, so now you would have a magnet. Okay, so magnet, okay, no magnet, disorganized, organized. So in order for them to be a magnet, they have to have an organized domain. So a permanent magnet or a magnet can be made by placing a magnetic material. So if you want to actually make a magnet, You place some kind of material like iron or something like that in a strong magnetic field. Okay, so something that has those electrons that have that capability of becoming a magnet, place it in a strong magnetic field. The strong magnetic field then causes those magnetic domains, those little clusters, to line up. You want them to get organized. You want them to be in a perfect row. Okay, and these perfect rows then make it so now that they have magnetic properties. Okay. Alright, so that's how you make a permanent magnet. You make a disorganized situation organized. You clean up your room, basically. Okay. So basically what happens is that because there's not room for movement, everything is perfectly organized, it becomes a permanent magnet. Now, if you want to undo a permanent magnet, you heat it. Okay, if you heat it, then you are able to basically use the word jostle domains out of alignment, and then basically you will no longer have a magnet. So if you don't want a magnet to any longer be a magnet, or something's magnetized and you're like, I don't want this to be a magnet anymore, just heat it up. Okay. Can a pole be isolated? Can you only have a South Pole or only have a North Pole? Can these poles be on their own? Okay. Is that possible? No. Every magnet, no matter what, if it's a South Pole, a North, every magnet will, if you cut it into smaller and smaller pieces, will always have a North and a South Pole. You cannot isolate a pole.